The universe is not a collection of isolated islands. It is a single, living structure. This is the cosmic web, the fundamental architecture of everything. For most of history, the vast darkness between galaxies seemed empty and silent. We now know that blackness is an illusion. It is filled with massive, faintly glowing strands of gas, stretching for millions of light years. These filaments connect every galaxy in a dynamic, breathing network. The central mystery is how we found these invisible threads, what they are made of, and how they act as cosmic rivers feeding stars and planets. By the end, you will understand the hidden skeleton that shapes the entire cosmos. This discovery solves a fundamental puzzle about where most of the universe's normal matter has been hiding. How did we first glimpse a structure that was predicted but never seen? What does it mean that our home galaxy is just one knot in this vast, glowing tapestry? What does this hidden architecture reveal about our own place in the story of everything? For most of human history, we looked up and saw a sky full of scattered, lonely lights. We grouped those lights into constellations, but we imagined each galaxy as its own isolated island universe, floating in an endless, empty sea of nothing. This picture was comforting in its simplicity, but it was fundamentally wrong. The universe is not a random, sparse collection of objects. It has a structure, a breathtaking architecture on the largest scales imaginable. This is the cosmic web. Picture the universe not as a dark ocean, but as a single, colossal living organism. Its bones are the dense clusters where thousands of galaxies swarm together. Its vast, empty lungs are the tremendous voids, regions of space spanning hundreds of millions of light years that are almost completely devoid of galaxies. And connecting these bones and these empty spaces, like a network of luminous tendons and capillaries, are the filaments. These are the massive strands of glowing gas. They form the scaffolding upon which everything we see is built. Every galaxy, every star cluster, every solitary spiral like our own Milky Way is simply a knot tied into this universal net. This is not a metaphor. It is the physical, large-scale structure of our cosmos, revealed by painstaking observations and sophisticated computer simulations. To visualize it, think of the intricate network of neurons in a human brain, with bright cell bodies connected by long, thin axons. Or think of the structure of a sponge, with solid material forming an interconnected lattice surrounding pockets of empty space. The cosmic web is the sponge, and we live within its delicate, glowing walls. For decades, this web was a beautiful theory, a prediction born from our understanding of gravity and the aftermath of the Big Bang. We could see the dense clusters of galaxies, and we could map the enormous voids, but the filaments themselves, the very threads that sew the universe together, remained invisible, hidden in the darkness between the bright lights. They were the missing piece of the puzzle, the ghostly architecture we knew must be there but could not directly touch. Finding this ghostly architecture was the great observational challenge of modern cosmology. The filaments are not made of stars. They are not solid or dense like a nebula. Instead, they are woven from two invisible substances. The first is dark matter, the mysterious, unseen mass that provides the gravitational skeleton for the entire web. The second is the normal matter that follows the dark matter's lead, a diffuse, superheated gas known as the warm-hot intergalactic medium. Scientists call it the WIM. This gas is so thin, so spread out across millions of light years, that a single cubic meter of it might contain only a single atom. Yet across such vast distances, it adds up to an astonishing amount of material. The problem was seeing it. This gas does not glow like a neon sign. It is not cold enough to form stars, nor is it hot enough to shine with the fierce, specific light of a quasar. It exists in a difficult middle state, emitting only an extremely faint general ultraviolet glow. For traditional telescopes, it was like trying to see a single, dim light bulb from across an entire city. The glow was lost in the overwhelming darkness. Astronomers had maps from simulations showing exactly where the filaments should be. They could see the galaxies at the intersections, like bright beads on an invisible string. But the string itself remained maddeningly out of sight. The hunt required a new kind of tool and a completely new strategy. The breakthrough came not from building a bigger telescope to look deeper, but from building a more sensitive instrument to look at what was already right in front of us in a different way. The solution was to borrow a light from the most powerful beacons in the cosmos. Quasars are the hearts of distant galaxies, powered by supermassive black holes feeding on enormous amounts of material. The process is so violent, so energetic, that a single quasar can outshine its entire home galaxy by a factor of 1,000. From our perspective, they appear as impossibly bright, pinpoint stars, shining from the very edge of the observable universe. Astronomers realized these quasars could serve as the ultimate cosmic flashlights. By pointing a powerful telescope at a quasar, they weren't just studying the quasar itself. They were using its brilliant beam to illuminate everything that lay in the vast, dark space between it and us. Think of it like driving at night. Your headlights don't just light up the road 100 feet ahead. They also illuminate the fog and the rain in the beam's path, revealing the texture of the very air you are moving through. A quasar's light does the same thing on a cosmic scale. As that pristine light travels for billions of years across the universe, it passes through the diffuse gas of the cosmic web. Atoms within that gas, hydrogen, helium, oxygen, are particular. They absorb light only at very specific colors or wavelengths. When the quasar's light finally reaches our telescopes, astronomers break it apart into a full rainbow, a spectrum. They then search for dark lines, tiny gaps in that rainbow where specific colors have been stolen. Each dark line is a chemical fingerprint, a definitive sign that the light passed through a cloud of a certain gas at a specific distance. This technique, called absorption line spectroscopy, gave us our first real evidence of the stuff between the galaxies, but it had a significant limitation. The beam of light from a single quasar is incredibly narrow, like a pencil-thin laser pointer shot across the universe. It only samples a one-dimensional line through the vast, three-dimensional web. It might pierce a single filament, revealing a gas cloud at one precise point, but it tells us nothing about the shape, the size, or the connected structure of that filament. It was like trying to map a giant, intricate spiderweb by touching it with a single, very long needle. You would know the web was there, but you could never see its beautiful, interconnected form. The hunt required a new approach, one that could move from probing single points to finally illuminating the entire hidden tapestry. The invisible map was finally drawn not by a telescope, but by a machine. While observers struggled to see the faintest hints of the web, a parallel revolution was unfolding inside the world's most powerful supercomputers. This was the era of the cosmological simulation, and it gave us the first complete vision of the universe's hidden skeleton. Projects with names like the Millennium Run and IllustrisTNG began with a simple, audacious premise. They would create a virtual universe from scratch. Scientists would feed the computer the known laws of physics, the precise recipe of dark matter and normal matter from the Big Bang, and then press play. The simulation would then fast-forward the clock, modeling 13.8 billion years of cosmic evolution in a matter of months. The process hinges on gravity's relentless pull. In the early, almost smooth universe, tiny ripples in density serve as seeds. Dark matter, responding only to gravity, begins to clump around these seeds. Over eons, these clumps grow, merge, and stretch into vast sheets and long, tendril-like chains. Normal matter, the gas that will one day form stars, is then pulled along this invisible dark matter scaffold. What emerged from these digital universes was breathtaking and consistent. Every single time, no matter the slight variations in the starting conditions, the same structure formed. A magnificent cosmic web with dense clusters, empty voids, and most importantly, the intricate connecting filaments. The simulations did more than just predict the shape. They calculated the physical state of the gas trapped in those filaments. They told observers it would be extremely diffuse, heated to temperatures of hundreds of thousands of degrees, and that it should glow with a very specific, faint ultraviolet light. This was the game-changing roadmap. Astronomers were no longer searching the darkness for a ghost. They now had a detailed prediction of the ghost's height, its weight, the clothes it was wearing, and exactly which street corner it should be standing on. The hunt could move from speculation to a targeted search. We had the blueprint. Now we needed to turn on the lights and see the building for ourselves. The roadmap from the simulations pointed to a specific patch of sky. Astronomers using the Very Large Telescope in Chile focused its newest eye, an instrument called MUSE, on a region where two massive galaxy clusters were slowly drifting toward one another. Between them, according to every simulation, there should be a thick filament of the cosmic web, a bridge of gas pulled taut by the immense gravity of the clusters on either end. This was the perfect place to look, but how do you see something that emits almost no light of its own? The team devised a clever new strategy, moving beyond the single quasar flashlight. Instead of one brilliant beacon, they would use the combined glow of millions of faint, distant galaxies. These were galaxies from the early universe, filled with hot, newborn stars pouring out ultraviolet light. This collective starlight, though faint from any single galaxy, created a diffuse, cosmic background glow all across that region of space. Think of it like a cloudy day. You are not seeing the sun directly, but the entire sky is softly illuminated. That ambient ultraviolet glow was the key. As this light washed over the predicted filament, it did something extraordinary. It caused the hydrogen atoms within that diffuse gas to fluoresce. The atoms absorbed the ultraviolet light and re-emitted it at one very specific color, a wavelength known as Lyman-alpha. It is a signature glow of hydrogen, the universe's most basic element. The MUSE instrument is a phenomenal tool for this exact task. It does not just take a picture. It captures a full spectrum of light for every single pixel in its image, allowing it to isolate that specific, faint Lyman-alpha glow from all the other light in the scene. When the team processed the data, filtering out everything except that one color, the hidden structure snapped into view. There it was, a faint, luminous tendril of hydrogen gas stretching across the vast darkness. It was not a point, not a line from a quasar beam. It was a two-dimensional image of the cosmic web itself, a glowing filament millions of light-years long, directly connecting the two galaxy clusters just as the simulations had foretold. This was the first light, the moment the invisible skeleton of the universe was revealed to human eyes. The image was not a colorful, detailed photograph. It was a map of pure presence, a ghostly outline traced in the faint emission of primordial hydrogen. It confirmed that the filaments were real, that they contained the long-sought missing matter, and that they were structured exactly as our models of cosmic evolution demanded. This single observation transformed the cosmic web from a compelling theoretical prediction into an observed physical reality. We had finally seen the threads of the tapestry. That faint, ghostly glow is the signature of the universe's most fundamental material. The filaments of the cosmic web are woven from the same basic ingredients that make up you, me, and every star we see in the night sky. This is ordinary matter, the stuff of atoms, which scientists call baryonic matter. It is not the mysterious dark matter that forms the web's invisible gravitational skeleton. Instead, it is the luminous trace of the normal universe, finally revealing where most of it has been hiding. The primary element at work here is hydrogen, the simplest and oldest atom, forged in the first moments after the Big Bang. This is not the cool, dense hydrogen of a stellar nursery, however. The gas within these cosmic threads has been stretched, heated, and energized by the immense forces shaping the web. It exists as a superheated plasma with temperatures ranging from 100,000 to 10 million degrees Celsius. At these extremes, atoms cannot hold onto their electrons. They are torn apart, becoming a soup of positively charged atomic nuclei and free electrons. Scientists have a name for this elusive state of matter, the warm-hot intergalactic medium, or the WIM. This hot, thin plasma is so diffuse that it is a better vacuum than anything we can create in laboratories on Earth. Yet across the staggering distances of a filament, it contains more ordinary matter than all the stars in all the galaxies combined. It is the universe's hidden reservoir. This ionized gas does not glow with visible light. Instead, it emits energy in more extreme parts of the spectrum, in the form of faint ultraviolet and soft X-ray radiation. This is the specific signal that our most sensitive space telescopes were built to find. It is a whisper of high-energy light, a subtle fingerprint that finally allowed us to see the invisible. Understanding this composition solves a profound cosmic mystery. For decades, our inventories of normal matter in the nearby universe did not add up. When we counted all the atoms in stars, galaxies, and the cooler gas we could see, we found only about half of what the Big Bang theory predicted should exist. The other half was missing. The discovery of the WIM in the filaments is the answer. The missing atoms were not lost. They were simply hiding in plain sight, spread so thinly across the vast intergalactic voids that they were nearly impossible to detect. They have been there all along, tracing the grand design of the cosmos. This means the glowing strands are more than just a beautiful structure. They are the storage system for the universe's ordinary matter, and they hold the key to understanding how galaxies, including our own, came to be. For decades, this discrepancy was a quiet crisis in cosmology. We had two very different ways of counting the atoms in the universe, and they told two different stories. The first method looked back to the very beginning. The cosmic microwave background, that faint afterglow of the Big Bang, is like a baby picture of the cosmos. By studying its subtle patterns, scientists could calculate with incredible precision how much ordinary matter, or baryonic matter, existed when the universe was only 380,000 years old. It gave us a complete inventory of the atoms forged in the first moments. The second method was a modern-day census. Astronomers would add up all the normal matter they could see in the present-day universe, all the stars in all the galaxies, all the cold gas in nebulae, all the dust swirling around black holes. And every time they did the math, they came up short. The present-day count was only about half of what the baby picture said should be there. Where did the other half of the universe's atoms go? This was the missing Baryon problem, a glaring gap in our understanding of cosmic evolution. It suggested that either our reading of the primordial baby picture was wrong, or a staggering amount of the universe's basic building blocks had simply vanished into the darkness. The filaments and the warm-hot intergalactic medium within them provide the elegant solution. The missing atoms were never truly missing. They were simply hiding in a state we had not yet learned to see. They are not locked up in bright stars or dense planets. Instead, they are spread across the immense, lonely spaces between the galaxies, heated and ionized into that faint, diffuse plasma. When you account for the sheer volume of these cosmic threads, the math finally balances. The WIM in the filaments contains the vast majority of the normal matter in the nearby universe. This transforms our view of those glowing strands. They are not merely decorative features of the cosmic web. They are its primary storage system. They are the universe's attic, holding in reserve the raw material from which everything we see is built. The discovery of their faint glow was far more than just spotting a beautiful structure. It was the direct detection of a lost reservoir, the closing of a major chapter in cosmology. We found the atoms by finally learning how to see the architecture that contained them all along. This faint glow is a signal from the edge of perception, and capturing it requires instruments of almost impossible sensitivity. To move from a single, ghostly image to a true map of the cosmic web, astronomers have built a new generation of telescopes, both in space and on the highest mountaintops, each designed to catch a different whisper from the filaments. In space, the European Space Agency's XMM-Newton X-ray Observatory acts as a scanner for the hottest components of the web. It does not see visible light. Instead, it detects the high-energy X-ray photons emitted by gas heated to millions of degrees. When this observatory stares at the spaces between massive galaxy clusters, it can sometimes detect a faint, diffuse X-ray haze. This is the signature of the hottest plasma caught in the gravitational pull of the web's densest intersections, a direct confirmation that the filaments are not just theoretical lines but physical reservoirs of energetic matter. On the ground, a different approach captures the cooler but still extremely hot hydrogen. Instruments like the Keck Cosmic Web Imager, KCWI, at the W.M. Keck Observatory in Hawaii, and the Hyper-Subprime camera on the Subaru telescope in Japan are masters of a specific technique. They are incredibly sensitive spectrographs and cameras built to isolate the faint Lyman-alpha glow, that ultraviolet fingerprint of hydrogen fluorescence. Their immense mirrors collect as much of that elusive light as possible, and their optics are finely tuned to separate it from the overwhelming glare of nearby stars and galaxies. It is like trying to hear a single violin playing a soft note in a roaring concert hall. These instruments are the sensitive ears that finally pick out that delicate melody from the cosmic noise. Yet even with these technological marvels, a single observation of a filament is often too faint, too tenuous to provide a clear picture. The solution to this problem is both simple and profoundly clever. It is called stacking. Astronomers take the predicted locations of filaments from their supercomputer simulations. They then gather not one, but hundreds or even thousands of observations from different lines of sight, each one pointing at a different predicted filament. Individually, each image might show only a hint of a glow, a maybe, a statistical fluctuation. But when they digitally combine or stack all these images together, aligning them based on the simulated map, the true signal emerges. The random noise averages out, and the consistent, faint glow of the filament structure adds up. It is the ultimate exercise in patience and statistics, building a portrait of the universe's skeleton not from a single snapshot, but from the combined evidence of countless glances into the darkness. This technique has transformed our view. We are no longer looking for one ghost. We are assembling a census of phantoms, proving their existence through the overwhelming weight of collective evidence. The map is being drawn one stacked observation at a time, revealing that the glowing strands are not rare features, but the universal rule. These glowing strands are far more than a static map of the universe's past. They are its active circulatory system, a network of flowing rivers on the largest scale imaginable. The filaments of the cosmic web are dynamic highways, and they are constantly in motion, channeling the raw material for creation across the cosmos. Gravity is the engine of this vast transport network. The immense gravitational pull of a galaxy cluster, a massive knot in the web where thousands of galaxies swarm together, acts like a powerful cosmic drain. It pulls on the diffuse gas within the filaments that connect to it, setting that material in motion. The superheated plasma of the warm-hot intergalactic medium begins to flow, streaming along the filament's invisible magnetic and gravitational contours. Picture a great river system on Earth. Countless tiny tributaries in the mountains gather water, which then merges into larger streams, then into mighty rivers, all flowing relentlessly toward the sea. The cosmic web operates on the same principle, but the mountains are the slight density variations from the Big Bang. The rivers are the million light-year-long filaments, and the sea is a voracious galaxy cluster. This flow is not a gentle trickle. Simulations show it can reach astonishing speeds, with gas rushing along these intergalactic channels at hundreds of kilometers per second. This continuous delivery service is what sustains the universe's vibrant neighborhoods. Without it, a galaxy cluster would be a closed system. The galaxies within it would rapidly consume their available cold gas, forming a brilliant but short-lived burst of stars, and then fade into darkness as their fuel ran out. The flowing filaments prevent this cosmic burnout. They provide a constant, if subtle, influx of new material. This fresh gas can cool, condense, and eventually collapse to form new generations of stars within the cluster's galaxies. It is a slow and steady process, but over billions of years it is essential. It means the great cities of the universe are not isolated or self-consuming. They are fed by these long-distance supply lines, these rivers of primordial hydrogen and helium that have been flowing since the universe was young. This establishes the filaments as the fundamental supply lines of the cosmic economy. They govern growth, determine which regions thrive, and ensure that even the oldest structures continue to have a source of new life. This cosmic delivery system does more than just sustain existing galaxies. It is the very reason they exist in the first place. The glowing filaments we see today are not just highways, they are the ancient assembly lines upon which every galaxy was built. The story begins with the faintest whisper in the newborn universe. In the first moments after the Big Bang, the cosmos was not perfectly smooth. It was imprinted with tiny ripples, quantum fluctuations stretched to cosmic scales. These were the seeds of all future structure. Gravity is an amplifier of inequality. Where there was a slightly denser patch of dark matter, gravity pulled a little harder, attracting more dark matter from the surrounding area. Over hundreds of millions of years, this process sculpted the first ghostly framework. Dark matter, invisible and responsive only to gravity, wove itself into a vast network of thin sheets and intersecting strands. This was the primordial cosmic web, a scaffold of pure potential. Ordinary matter, the gas that would become stars and planets, was caught in this gravitational current. It flowed along the contours of the dark matter filaments, following the invisible valleys of gravitational potential. As this hydrogen and helium gas streamed into the filaments, something critical happened. The gas particles collided, creating friction and shock waves. This converted their motion into heat, but the vast, thin expanse of the filaments also allowed that heat to radiate away into space. The gas began to cool. Cooling gas loses energy and condenses. Think of steam rising from a hot road on a summer day. As it rises and cools, it condenses into visible clouds. On a cosmic scale, this cooling within the filaments caused the diffuse gas to pool and thicken, especially at the intersections where multiple strands met. These intersections, the nodes of the web, became the gravitational focal points. Here, the flows from different filaments converged, piling up vast reservoirs of cooled, dense gas. These dense knots, cradled in the heart of the dark matter scaffold, were the cradles of the first galaxies. They are known as proto-galaxies. Within these swirling, gas-rich pools, gravity continued its work, pulling the gas into ever denser clumps. When the density and pressure reached a critical threshold, nuclear fusion ignited in their cores. The first stars burst into existence, not in isolation, but in brilliant clusters, lighting up the nodes of the cosmic web. A filament, therefore, is much more than a bridge. It is an incubator and a conveyor belt. It gathered the raw material from the emptiness, guided it, cooled it, and delivered it to the construction sites where galaxies would be assembled. Our own Milky Way likely began its life in such a node, fed by the convergent flows of several ancient, glowing strands. Every majestic spiral and every elliptical giant we see today started as a whisper in the dark, grown to greatness along the luminous threads of the universal web. The faint glow we see is not a single color, but a symphony of light across the entire spectrum of energy. Each type of emission acts as a different instrument, revealing a unique layer of the filament's complex physical state. The most direct signal comes from hydrogen itself. When bathed in the ambient ultraviolet light of the early universe, the atoms within a filament can absorb and re-emit that energy. This produces a specific ultraviolet wavelength known as Lyman-alpha fluorescence. It is a gentle, resonant hum, a direct signature of the gas's presence and its interaction with the cosmic environment. This glow tells us where the gas is, and it is most sensitive to filaments that are relatively cooler and denser, where hydrogen atoms can still hold onto their electrons. For the hottest components of the web, we must listen to a much higher-pitched signal. Gas heated to millions of degrees by the immense gravitational forces of the web does not emit visible or ultraviolet light. Instead, it shines in X-rays. Space observatories like XMM-Newton scan the spaces between clusters, searching for a faint, diffuse haze of soft X-ray emission. This is the signature of electrons torn free from their atoms and moving at tremendous speeds, colliding with ions and releasing high-energy photons. Detecting this X-ray glow is like feeling the heat radiating from an invisible oven. It confirms the presence of an extremely energetic, thin plasma that would otherwise be completely dark to our eyes. There is a third, even more subtle way to sense the cosmic web, and it involves looking at the oldest light in the universe. The cosmic microwave background is the cooled remnant of the Big Bang's first flash, a nearly uniform glow that permeates all of space. As this ancient light travels for billions of years to reach us, it occasionally passes through a massive filament of hot gas. The incredibly energetic electrons within that filament interact with the microwave background photons in a specific way. They give the photons a tiny boost of energy, slightly distorting the background's uniform temperature in that particular direction. This is called the Sunyaev-Zeldovich effect. It does not produce a glow we can see, but rather a cold or hot spot in the detailed map of the microwave sky, a shadow cast by the hot electrons in the filament. Each of these signals, the ultraviolet fluorescence, the X-ray haze, and the microwave distortion, paints a different part of the picture. The Lyman-alpha shows us the cooler, denser streams. The X-rays reveal the scorching plasma at the intersections. The Sunyaev-Zeldovich effect traces the integrated pressure of hot electrons along our line of sight. By combining all these observations, astronomers are not just seeing a filament. They are taking its temperature, measuring its density, and understanding its energetic state. It is the difference between seeing a silhouette and performing a full medical scan, revealing the intricate inner workings of the universe's circulatory system. Even with our most powerful telescopes, the faint glow of the cosmic web is almost drowned out by the universe's own cacophony. The signal we are trying to detect is not just weak, it is profoundly contaminated. The first and most persistent source of noise comes from our own cosmic backyard. Our Milky Way galaxy is filled with a diffuse fog of gas and dust, which itself emits a faint, confusing light in the same ultraviolet and optical wavelengths we use to hunt for filaments. This foreground emission is like a persistent, glowing veil draped across the entire sky, and we must look through it to see the distant web. Then there are the galaxies themselves. When we point a telescope at a predicted filament, our field of view contains not just the empty space we are targeting, but also countless faint, distant galaxies that are too small and dim to be seen as individual points of light. Their collective starlight blends together into an unresolved background glow, adding another layer of contamination to the data. This is like trying to hear a whisper in a crowded, murmuring room. The signal from the filament is the whisper. The instrumental noise from the telescope's own electronics is a constant hiss, and the foreground light from our galaxy and the unresolved galaxies is the overwhelming murmur of the crowd. Separating the whisper from this chorus of interference is the central technical challenge of modern cosmology. It requires more than just sensitive instruments. It demands brilliant statistical detective work. Astronomers rely on a process called stacking, combining hundreds of observations of different predicted filaments to amplify the true signal while the random noise averages out. They also create intricate digital filters, algorithms designed to recognize and subtract the predictable patterns of foreground emission based on our detailed maps of the Milky Way. The final image of a filament is never a simple photograph. It is a statistical phantom, revealed only after painstakingly peeling away the universe's many brighter layers. This means our map of the cosmic web is by necessity a map of probability and inference. We see its outline not because it shines brightly for us, but because we have learned to listen for its specific, quiet frequency amidst the cosmic static. This statistical phantom reveals a universe built on a hierarchy of connections. To truly understand the scale of these glowing rivers, we must pull our perspective back even further, out beyond the clusters and the long, lonely filaments. We must zoom out to the grandest neighborhoods in the cosmos, the superclusters. These are the continents of the universe, the largest known structures that gravity has bound together. A supercluster is not a single, dense object. It is a sprawling metropolis of galaxy groups and clusters, all interconnected by a network of particularly massive and dense filaments. Our own home, the Milky Way, resides within one such structure, the Laniakea supercluster. The name is Hawaiian for immense heaven, and it is a fitting title for a structure that spans over 500 million light-years and contains the mass of 100 quadrillion suns. Within Laniakea, we are not at the center, but rather on the outskirts, flowing along a celestial current toward a much denser region. The entire supercluster is defined by its gravitational watershed, the area from which all galaxies are slowly streaming toward a central point of attraction known as the Great Attractor. This motion is not random. It is channeled along the supercluster's own internal web. One of the most prominent features within Laniakea is a colossal filament, a river of galaxies and intergalactic gas that flows directly into the immense Virgo cluster, one of the supercluster's core hubs. This filament is not a faint, distant thread. It is a local, bustling freeway of cosmic material, and it provides astronomers with an unparalleled laboratory. Because it is relatively close to us, we can study it in far greater detail than any filament seen at the edge of the observable universe. We can map the individual galaxies moving along its length, measure the temperatures and densities of its gas with higher precision, and observe how its gravitational pull shapes the motions of everything around it, including our own galactic neighborhood. Studying these local, larger filaments is like having a detailed street map of our own city, while the distant filaments we observe are like blurry satellite images of a foreign continent. By examining the physics of the Laniakea filament, we can test our models of how gas cools, how galaxies interact with the web, and how these massive structures influence cosmic evolution on the largest scales. It turns the abstract concept of the cosmic web into a tangible, nearby phenomenon that is actively shaping our place in the universe. But the flow of this cosmic river is not a one-way street. The filaments feed the galaxies, but the galaxies themselves are not passive recipients. They are dynamic engines, and they give back to the web in ways that fundamentally alter its chemistry and energy. This is the process of cosmic feedback, a powerful cycle that reshapes the very material that birthed them. The most dramatic form of feedback comes from the hearts of the galaxies themselves. At the center of most large galaxies, including our own Milky Way, lies a supermassive black hole. When such a black hole actively feeds on surrounding gas, it does not do so quietly. The infalling material swirls into a blazing disk of plasma, and from the poles of this disk, it can blast out colossal jets of particles and radiation moving at nearly the speed of light. This entire furious system is an active galactic nucleus, and its energy output can outshine its host galaxy. These jets and radiation plow directly into the surrounding environment. They act like cosmic blowtorches, heating the gas within the galaxy's halo and the nearby filaments to even more extreme temperatures. This intense heat can prevent the gas from cooling and collapsing to form new stars, effectively putting a limit on the galaxy's growth. In the most violent cases, these outflows can push vast quantities of enriched gas completely out of the galaxy, launching it back into the intergalactic medium. On a smaller but more frequent scale, stars themselves contribute to this feedback. Massive stars live fast and die young, ending their lives in titanic supernova explosions. Each of these stellar deaths is a cataclysm, releasing a shockwave of energy and ejecting newly forged heavy elements carbon, oxygen, iron, silicon out into the galaxy's surroundings. Over billions of years, countless supernovae act like a cosmic bellows, stirring and heating the gas within a galaxy and its immediate filamentary connections. They create vast, expanding bubbles of hot, metal-rich material that can eventually break free of the galaxy's gravitational pull. This process does more than just return gas to the web. It fundamentally changes the web's composition. The gas that originally flowed into the galaxy was pristine, composed almost entirely of hydrogen and helium from the Big Bang. The gas that is blown back out is polluted. It is seeded with the heavy elements forged in stellar cores and supernova furnaces. This enriched material then mixes back into the warm, hot intergalactic medium of the filaments. Over cosmic time, this feedback cycle means the filaments are no longer just rivers of primordial gas. They become recycling streams carrying the ashes of dead stars. This enrichment is crucial for the future of the cosmos. When this metal-polluted gas later flows into a new generation of galaxies, it provides the raw materials for rocky planets, complex chemistry, and ultimately the possibility of life. The web does not just build galaxies, it is continuously seasoned and energized by them in a grand, slow-motion exchange that ties the fate of stars to the architecture of the universe itself. That grand recycling process means the cosmic web we see today is not the same as the one that first lit up the darkness. It is a living structure, one that has evolved and matured across nearly 14 billion years. If we could rewind the universe and watch its skeleton take shape, we would witness a dramatic transformation from a smooth, almost featureless haze into the intricate, glowing lattice we now observe. The story begins with a universe that is remarkably uniform. For the first few 100 million years after the Big Bang, the cosmos is a warm, dense fog of hydrogen and helium plasma. There are no stars, no galaxies, and no filaments, but those tiny quantum ripples from the beginning are already at work, serving as the faint blueprints for everything to come. Gravity begins its slow, relentless sculpting. The slightly denser patches of dark matter pull in more dark matter from their surroundings. They do not form isolated clumps, however. Instead, they collapse into vast, interconnected sheets and walls like the foam in a bubble bath. Where these sheets intersect, they form long, dense lines. This is the birth of the filamentary network. In these early epochs, the web is a dense, chaotic tangle. The filaments themselves are thicker and more numerous, and the spaces between them, the voids, are much smaller. The gas flowing into this primordial scaffold is also different. It has not yet been processed by generations of stars. It is pristine, composed only of hydrogen and helium, and it is relatively cool. This allows it to condense and collapse into stars with astonishing efficiency, leading to the formation of the first brilliant galaxies at the web's intersections. As the eons pass, gravity's work becomes more focused and dramatic. It is a runaway process of consolidation. The larger knots in the web, the protoclusters, have stronger gravitational pulls. They act like cosmic magnets, drawing in not only nearby galaxies but also the gas from the filaments that feed them. This continuous inflow has two profound effects. First, the galaxy clusters themselves grow monstrously large, becoming the dense, shining cities of the universe. Second, as matter drains from the filaments into these clusters, the filaments themselves become thinner, more refined, and more clearly defined. Simultaneously, the voids between the filaments expand. As matter streams out of these regions toward the gravitational wells of the web, the voids become ever emptier, growing into the vast, desolate deserts that characterize the modern cosmos. This evolution is beautifully captured in supercomputer simulations. If you watch a time-lapse of a simulated universe, you see the initial, fine web of the early cosmos, looking almost like a delicate sponge. Over time, that sponge stretches, the dense knots brighten and coalesce, the filaments elongate and sharpen, becoming the distinct rivers connecting the now distant clusters. The voids blow up like balloons, pushing the web's structure into sharper relief. The final transformative force is the feedback we just discussed. The early, cool gas in the filaments is gradually heated. The fierce radiation from the first stars and quasars, and later the supernova explosions and black hole jets from billions of galaxies, pump enormous energy back into the intergalactic medium. This feedback raises the temperature of the gas within the filaments from tens of thousands of degrees to millions of degrees, transforming it into the warm-hot intergalactic medium we struggle to detect today. This heating makes the modern web more subtle. It prevents the gas from cooling as easily, slowing down the frantic star formation of the early universe and regulating the growth of galaxies. The web we inhabit now is therefore an older, more spread out, and more energetic version of its youthful self. It has transitioned from a hotbed of frantic construction to a mature, regulated network, one that still feeds growth but does so with the steady, measured pace of an established universe. The glowing gas we see is only the luminous echo of a far more powerful presence. This entire magnificent structure, from the thinnest tendril to the densest cluster, owes its existence to an invisible force. The filaments of ordinary matter are luminous tracers, following roads laid down by dark matter. Without this mysterious substance, the cosmic web as we know it could never have formed. In the early universe, ordinary matter faced a significant obstacle to clumping together. After the Big Bang, the cosmos was a searing plasma of particles and intense radiation. This radiation exerted immense pressure, smoothing out any attempts by normal matter to collapse under its own gravity. It was like trying to build a sandcastle while waves constantly washed over the beach. Dark matter provided the solution. Unlike normal atoms, dark matter does not interact with light or radiation. It is invisible and, for all practical purposes, oblivious to that early cosmic pressure. It feels only the pull of gravity. This meant that while normal matter was being buffeted by radiation, dark matter could begin to clump together undisturbed. It acted as a gravitational anchor, forming the first faint seeds of structure in the primordial darkness. As these dark matter seeds grew, they created deep gravitational wells, pockets of intense pull in the fabric of space. Only then could normal matter, once the universe had cooled and expanded enough for radiation's pressure to fade, begin to fall into these pre-existing wells. The hydrogen and helium gas flowed along the contours of this invisible dark matter landscape, pooling in the valleys and streaming along the ridges. The filaments of glowing gas are therefore a direct imprint, a map in light of the underlying dark matter skeleton. Where we see a luminous strand of the warm-hot intergalactic medium, we know there is a denser, thicker filament of dark matter beneath it, guiding its shape and holding it together with its immense, unseen gravity. This relationship provides astronomers with one of the most powerful tools in modern cosmology. By carefully mapping the distribution of the faintly glowing gas, using techniques like stacking and spectral analysis, they are not just studying ordinary matter. They are indirectly charting the architecture of the dark universe. They can measure how the gas clumps and flows, and from that, infer the shape and mass of the invisible dark matter scaffold that dictates every motion. This offers a crucial real-world test for our theories of dark matter. Different models predict slightly different behaviors for how dark matter should cluster and how it should guide the gas flowing through it. The precise maps we are now creating of the cosmic web's luminous strands serve as a physical benchmark. They allow scientists to check which theoretical models accurately reproduce the delicate, filamentary patterns we observe in the real sky. In this way, the faint glow of intergalactic hydrogen becomes a flashlight shone not just into empty space, but into the heart of one of physics' greatest mysteries. We are using the visible universe to decipher the rules of the invisible one, tracing the outline of the hidden hand that shaped everything. The map we are drawing reveals more than just expected structure, it uncovers profound puzzles. Some of these luminous filaments shine far brighter than our most sophisticated computer simulations predict. Their glow, especially in the Lyman-alpha ultraviolet light, is not a faint whisper but a clear, resonant hum, stretching across distances that challenge our understanding of cosmic physics. This unexpected brightness suggests there is more energy within these strands than our current models of the warm-hot intergalactic medium can explain. It is as if we discovered a river not just flowing but sparkling with its own internal light source, a phenomenon we have not yet fully accounted for. The mystery deepens when we consider the sheer coherence of these structures. According to basic physics, gas flowing at hundreds of kilometers per second over millions of light years should create tremendous shock waves. These shocks, like sonic booms on a cosmic scale, should heat the gas to extreme temperatures, potentially disrupting the filament's delicate structure and halting the smooth flow of material. Yet observations show many filaments remain remarkably intact and coherent. This presents a fascinating question. How does this cosmic plumbing maintain its integrity? How does the gas stay cool enough or calm enough to continue its journey without being torn apart by the very forces that set it in motion? One compelling line of investigation points to magnetic fields. While incredibly weak by Earth standards, vast, thread-like magnetic fields may be woven through the filaments themselves. These fields could act as a guiding sheath, channeling the flow of ionized gas and preventing turbulent mixing and excessive heating. They might provide the cosmic equivalent of riverbanks, keeping the flow focused and orderly over staggering distances. Another puzzle lies in the chemical makeup of the filaments. While primarily hydrogen and helium, the feedback from galaxies constantly enriches the web with heavier elements. Our observations are now sensitive enough to begin searching for the fingerprints of oxygen, carbon, and nitrogen within the intergalactic medium. Finding these elements in specific patterns or unexpected abundances could tell us new stories about how and when galaxies ejected their material, revising our timeline of cosmic recycling. Each of these anomalies, the unexplained glows, the coherent flows, the hints of hidden magnetic forces and unexpected chemistry, is not a failure of our science. They are guideposts. They highlight the limits of our current simulations and point toward richer, more complex physics at play within the universe's veins. Every discrepancy is an invitation to look deeper, to build better models, and to listen more carefully to the faint song of the cosmic web. These puzzles will soon be met by a new generation of eyes. The faint glow of the cosmic web is about to be illuminated as never before by a suite of observatories currently launching or in development, each designed to answer the specific questions our current tools have raised. The first of these revolutionary instruments is already in space, the James Webb Space Telescope. While famous for its stunning images of early galaxies, Webb possesses a unique capability crucial for Webb science: its powerful infrared vision. Webb can look back to a time when the universe was only a few 100 million years old to see the filaments in their infancy. At these extreme distances, the expansion of the universe has stretched the ultraviolet Lyman-alpha glow of hydrogen deep into the infrared part of the spectrum, where Webb excels. It can search for the fluorescent signature of hydrogen in the earliest strands, tracing how pristine gas first flowed into the nodes that birthed the very first galaxies. Webb is not just looking at the ancient web, it is looking at its moment of creation, helping us understand the initial conditions that set the entire structure in motion. While Webb peers deeply into specific patches of the ancient sky, another upcoming observatory will cast the widest possible net. The Nancy Grace Roman Space Telescope, set to launch later this decade, will perform a monumental wide-field survey. Its field of view will be 100 times larger than that of the Hubble Space Telescope. This vast perspective is the key to moving from studying individual filaments to creating a true census of the cosmic web. Roman will map the positions and distances of millions of galaxies with exquisite precision. This three-dimensional map will allow scientists to infer the underlying dark matter skeleton with unprecedented clarity, predicting exactly where the luminous filaments of gas should be. More importantly, Roman's wide-field cameras can then be used to stack thousands of these predicted locations, building a statistical portrait of the web's glow across enormous volumes of the universe. It will tell us if the unexpectedly bright filaments we have spotted are rare, or if they represent the standard state of the universe's plumbing. To understand the physical state of the gas within those filaments, we must sense their heat. This is the domain of a new class of X-ray observatories currently on the drawing board, missions like the European Space Agency's Athena and the proposed LINX concept. These are not general-purpose telescopes. They are specialized instruments built with one primary goal: to detect the faint, diffuse X-ray glow of the warm-hot intergalactic medium with a sensitivity 50 to 100 times greater than current observatories. Where today we might see a faint haze between two massive clusters, Athena and LINX will see detailed structure. They will map the temperature and density of the hot plasma as it flows along a filament, directly observing the shock waves and turbulence predicted by simulations. They will be able to trace how black hole feedback from galaxies heats and enriches the surrounding web, and potentially even detect the weak magnetic fields that may guide these cosmic currents. These observatories will shift our study from simply confirming the web's existence to performing a detailed diagnostic of its health, energy, and dynamics. Together, this next generation of tools represents a holistic approach to cosmic anatomy. Webb provides the deep time prenatal scan, Roman creates the full body structural map. And the advanced X-ray observatories will conduct the detailed blood test, analyzing the chemistry and energy of the universe's circulatory system. Within the next 2 decades, the faint, statistical phantom of the cosmic web will solidify into a high-definition movie, showing us not just where it is, but how it breathes, flows, and evolves. We stand on the verge of turning this grand theoretical architecture into a richly detailed, observable component of our reality, finally seeing the full majesty of the skeleton that holds up the sky. The supercomputer simulations gave us the map, but the telescopes are now providing the ground truth. This creates a fascinating and productive tension, a continuous dialogue between prediction and observation that is refining our understanding of the universe's most fundamental architecture. The agreement on the large-scale shape of the cosmic web is a triumph of modern cosmology. The simulations predicted a universe woven into a vast filamentary sponge, and our observations have now directly confirmed that exact structure. The fact that we can point a telescope at a predicted filament and see its faint, fluorescent glow is a powerful validation of our core theories of gravity and cosmic evolution. It tells us we are fundamentally on the right track in understanding how dark matter sculpts the cosmos. Yet the real science begins in the details, in the precise physical state of the gas within those glowing strands. Here, in the realm of temperature, density, and ionization, the conversation between simulations and reality becomes a meticulous process of calibration. The early simulations provided a broad brush prediction. The warm-hot intergalactic medium should exist and it should be hot. But how hot exactly? And is that heat distributed evenly, or are there pockets of cooler, denser gas within the filaments? Observations from instruments like the Keck Cosmic Web Imager are now measuring these properties. In many cases, they find beautiful agreement. The predicted Lyman-alpha glow is detected at the expected strengths and locations, confirming the general model of gas following the dark matter scaffold. However, subtle discrepancies are emerging that are just as valuable. Some filaments appear slightly brighter or more coherent than the simulations anticipated. This could mean the gas is a little cooler or denser in places than the models assumed. Other observations suggest the distribution of gas might be smoother or more clumped than predicted. Each of these minor mismatches is not a failure but a clue. It points to physical processes that our simulations may be simplifying or missing altogether. The most likely candidate for these refinements is the complex ballet of cosmic feedback. Our models of how energy from supernova and black hole jets is injected back into the intergalactic medium are incredibly complex approximations. They must account for the timing, the power, and the distribution of this energy across millions of light years. If a real filament is brighter than simulated, it might suggest that our feedback models are too violent, heating and dispersing the gas more than what actually occurs in nature. Perhaps magnetic fields, which are notoriously difficult to model on such large scales, are playing a more significant role in confining and channeling the gas, keeping it coherent and slightly cooler. Alternatively, a discrepancy might reveal an overlooked source of ionization, something else illuminating the hydrogen from within the filament itself. This iterative process is how science progresses. The simulations make a prediction, observations test it, the discrepancies are analyzed, leading to refined physics being coded into the next generation of simulations. Then those new, improved models make new, sharper predictions, which are again tested against the sky. This cycle is currently narrowing in on the true behavior of the gas that flows through the universe's veins. It is transforming the cosmic web from a static map into a dynamic physical system, whose properties we are measuring with ever-increasing precision. The ultimate goal is a perfect conversation, where what we simulate and what we observe tell the same detailed story, giving us a complete understanding of the forces that built and maintain the cosmic landscape we call home. This dialogue between simulation and observation leads us to a profound and humbling question. Is the magnificent cosmic web we inhabit a universal blueprint, or is it a unique and special arrangement, one that perhaps even allowed for our own existence? From our single vantage point, it is easy to assume this intricate lattice is the default architecture of reality. Yet the web's very existence hinges on a precise and delicate cosmic recipe. Its form is not an accident, but a direct consequence of the universe's opening moments and the specific nature of its unseen ingredients. The initial seeds were planted during a period of exponential expansion called cosmic inflation. This event stretched microscopic quantum fluctuations to cosmic scales, creating the slight density variations that would later become the gravitational anchors for all structure. Without these specific initial conditions, a smooth but not perfectly smooth beginning, the universe might have remained a formless haze or collapsed into a chaotic mess of black holes. The web then grew according to the rules dictated by the universe's contents, primarily the cold, collisionless nature of dark matter. This specific type of dark matter clumps in a hierarchical way, slowly building filaments and nodes over billions of years. If dark matter behaved differently, if it were warm or interacted strongly with itself, the resulting large-scale structure would be vastly altered, perhaps preventing the formation of such a clean, filamentary network. Given this recipe, however, the outcome seems almost inevitable. In any hypothetical universe that begins with similar inflationary wrinkles and is dominated by similar cold dark matter, gravity's relentless pull would almost certainly sculpt a cosmic web. The scale might differ, the timing might vary, but the fundamental architecture of clusters, filaments, and voids would likely emerge as a universal signature of that particular set of physical laws. This perspective challenges any notion of our web being specially crafted. It appears as a natural, almost mechanical consequence of the physics we observe. Yet this very universality highlights a deeper layer of fine-tuning. We can imagine theoretical alternatives where such rich structure never forms. Consider a universe where dark energy, the force driving cosmic acceleration, was vastly more powerful from the start. In such a scenario, expansion would have become dominant so quickly that gravity never had a chance to pull matter together into galaxies, let alone a web. The universe would be a thin, ever-diluting soup of isolated particles, forever dark and sterile. Or imagine a cosmos where the initial density fluctuations were much stronger. Structure might form too quickly and violently, collapsing everything into enormous black holes before delicate filaments could even be sketched. The fact that we live in a universe that produced this specific, structured web, one that could incubate galaxies and within them stars and planets, invites reflection. While the web itself may be a common outcome of certain physics, the particular physics we have appears to be precisely the set that allows for complexity and, ultimately, observers. We are not looking at a special web in a random universe, but perhaps at a necessary web within a universe whose laws are special. This shifts the wonder from the architecture itself to the underlying rules that made such architecture possible, rules that permitted the slow, beautiful construction of a universe capable of looking back at its own luminous skeleton. This magnificent, flowing architecture will not last forever. The cosmic web exists in a delicate balance between two titanic forces, the relentless pull of gravity that builds structure and the mysterious push of dark energy that is now tearing the universe apart. For billions of years, gravity held the upper hand, patiently sculpting the dark matter skeleton and drawing gas along the luminous filaments. But roughly 5 billion years ago, a fundamental shift occurred. Dark energy, a property of empty space itself that causes a repulsive gravitational effect, became the dominant force in the cosmos. This marked the beginning of the universe's accelerated expansion, a process that is now stretching the very fabric of space at an ever-increasing rate. This acceleration does not immediately destroy the web. The gravitational bonds within galaxy clusters, and even within our own local group of galaxies, are strong enough to resist the cosmic pull. But on the largest scales, the scales of the superclusters and the vast filaments that connect them, dark energy is the ultimate victor. It acts against the growth of new structure. Where gravity pulls matter together to thicken the filaments, The accelerating expansion of space works to pull it apart, stretching and diluting the intergalactic medium over colossal distances. The future of the cosmic web is one of slow, inevitable dissolution. Imagine a great city built along a mighty river. For ages, the river provides water, transport, and life, allowing the city to flourish. But if the climate changes and a great drought sets in, the river will gradually shrink. Its flow will weaken, its channels will become parched and faint, until one day it is nothing but a dry, forgotten bed. The river of gas between the cosmic cities will suffer a similar fate, not from drought, but from an ever-widening ocean of nothingness. In the far future, measured in tens or hundreds of billions of years, the consequences will be profound. The growth of the cosmic web will first halt and then reverse. The faint, glowing filaments that currently channel gas will be stretched by the expansion of space. They will become ever more tenuous, their atoms spread farther and farther apart. The warm, hot intergalactic medium will cool and dilute, its faint glow fading below any conceivable level of detection. The flow of gas, the lifeblood of galaxy clusters, will slow to a trickle and then cease entirely. Each great cluster of galaxies, along with its bound group of satellite galaxies, will become an isolated island universe, floating in an ever-darkening and ever more empty sea. Their internal connections will remain, but the long-distance bridges to other island clusters will have been severed by the expanding void. No new material will arrive from the intergalactic wilderness. The galaxies within these isolated clusters will continue to consume the remaining gas, but when it is gone, star formation will sputter out. The galaxies will age, redden, and fade. This casts our present epoch in a startling new light. We are living in the cosmic web's golden age. Right now, at this very moment in the universe's 13.8 billion year history, the web is at its most active and most observable. The filaments have formed and matured. They are still thick enough and bright enough for us to detect with our most ingenious instruments. Gas still flows along them, feeding the growth of galaxies. The great cities of the cosmos are still connected by luminous highways. We are witnessing the universe in its prime, a time of connection and construction, before the accelerating expansion severs those ties for all time. This realization adds a layer of profound privilege to our scientific quest. We are not just mapping a static feature of the cosmos. We are documenting a vibrant, dynamic phase that is transient. The faint glow we struggle to see is not merely a hidden structure. It is a signature of a cosmic era that will one day pass. Our ability to see the web at all is a gift of timing, a fleeting opportunity to observe the universe while it is still woven together. This cosmic perspective places life itself within the grand flow of the universal web. If the filaments are the supply lines and galaxies are the factories, then planets and the life they may hold are among the most intricate products of this entire system. The structure of the cosmic web does not merely create galaxies. It regulates the very conditions necessary for complex chemistry and, ultimately, biology to arise. Consider the alternative. In a universe without this efficient large-scale transport, matter could have been distributed in two equally sterile ways. The primordial gas might have remained almost perfectly smooth, spread so thinly across the cosmos that gravity could never gather it into the dense knots needed to ignite stars. Or conversely, the pull of dark matter might have been too effective, locking nearly all normal matter into a few monstrous, early black holes or into impossibly dense and violent clusters, leaving no quiet corners for stable solar systems to form. The cosmic web provides a middle path, a regulated delivery system. It gathers material from the voids and channels it steadily, but not too quickly, into galactic construction zones. This pacing is crucial. A torrent of cold gas flooding into a galaxy would trigger ferocious, unstable star formation, leading to constant supernova chaos that would sterilize any nascent planetary systems. The web's filaments, however, deliver gas at a more measured rate, often as a hot, diffuse flow that must first cool and settle. This allows for the sustained, multi-billion-year star formation history we see in galaxies like our Milky Way, where generations of stars live and die, enriching the galactic environment with heavy elements without overwhelming it. Those heavy elements, the carbon, oxygen, iron, and nitrogen forged in stellar cores, are the building blocks of rocky planets, oceans, and organic molecules. They are created inside stars and then scattered into space by supernova and stellar winds, a process of enrichment that depends entirely on the long-term, regulated life cycle of a galaxy. That galactic life cycle, in turn, is sustained by the web's continuous, if subtle, replenishment. Without the filaments acting as a galactic backup reservoir, a galaxy would exhaust its fuel on a cosmically short timescale, halting the production of new elements and leaving behind a static, aging stellar population with little potential for new Earth-like worlds. Therefore, the possibility of a rocky planet with liquid water and complex chemistry is not just a local accident, it is an indirect product of this universal architecture. The web's large-scale flows ensure that galaxies have both the time and the material diversity needed to forge the ingredients for life. It means that when we look up at the stars, we are not just looking at distant points of light. We are seeing the endpoints of a delivery chain that spans the entire observable universe, a chain that ultimately brought together the specific atoms that now form our world and ourselves. Our existence is a testament to the efficiency of this cosmic logistics network, suggesting that life, wherever it may arise, is fundamentally connected to the flowing rivers of the cosmic web. Mapping this universal architecture is not a task for professional astronomers alone. It is a challenge so vast, requiring the analysis of such immense volumes of data, that it has opened its doors to a global community of curious minds. The hunt for the faint, glowing strands of the cosmic web has become a pioneering frontier in citizen science, where anyone with a computer and an internet connection can contribute to a fundamental discovery. The data exists in staggering abundance. Space telescopes like Hubble have spent decades imaging the deep sky, while ground-based surveys like the Sloan Digital Sky Survey have meticulously catalogued the positions and colors of hundreds of millions of galaxies. This creates a three-dimensional map of the universe's luminous landmarks, but finding the faint gas that connects them is like trying to trace the pattern of a spiderweb from only the points where it touches a window frame. The filaments themselves are hidden within the darkness between the data points. This is where human intuition and pattern recognition become invaluable. Projects like Galaxies Zoo and its successors have demonstrated the incredible power of the public eye. Volunteers are presented with images of galaxies and asked to classify their shapes, a task where the human brain still outperforms even the most sophisticated algorithms in spotting subtle, unexpected features. This same collaborative model is now being applied to the cosmic web. Scientists are creating online platforms where volunteers can examine processed images from these vast astronomical archives, searching for the faint, diffuse smudges and elongated glows that might signal a filament bridging the gap between two galaxy clusters. It is a cosmic version of Connect the Dots, but where the dots are galaxies and the lines are ethereal rivers of gas a million light-years wide. The human ability to recognize patterns, especially faint and irregular ones, is a perfect complement to automated computer searches. An algorithm might be programmed to look for a specific predicted signal, but a person might notice an unusual wisp or a curious alignment that the algorithm was not designed to catch, potentially pointing toward a new type of structure or an unexpected physical process. This collaboration extends beyond simple visual inspection. Some citizen science initiatives invite participants with coding skills to help develop and refine the very algorithms that sift through the data. By creating challenges or open-source projects, researchers can tap into a diverse pool of talent to improve pattern recognition software, making it better at isolating the cosmic web's delicate signal from the background noise of the universe. This transforms the search from a solitary scientific endeavor into a collective human project. Every volunteer classification, every flagged anomaly, and every line of contributed code becomes part of a global effort to trace the skeleton of the cosmos. It means that the next faint filament, the one that helps solve the puzzle of its unexpected brightness or its mysterious coherence, might not be found in a university lab first. It might be spotted by a teacher in Lisbon, a retiree in Tokyo, or a student in Buenos Aires, staring at their screen and seeing a ghostly thread in the data that no one had noticed before. In this way, the cosmic web does more than connect galaxies. It connects us, weaving our collective curiosity into the process of uncovering the universe's grandest design. The darkness between the stars is a grand illusion. With this new understanding, the next time you stand beneath a clear night sky, your perception of the cosmos will have forever changed. You are no longer looking at a flat, black canvas dotted with isolated points of light. You are gazing into a deep, three-dimensional ocean, its currents made visible. Each star you see is a part of our local galactic neighborhood, the Milky Way, which is itself just one luminous knot tied into an unfathomably larger structure. That profound blackness stretching from the handle of the Big Dipper to the glow of Orion's belt is not empty. It is threaded with the faint, ultraviolet glow of ancient hydrogen, a filament in the local web. The Andromeda Galaxy, a faint smudge to the naked eye, is not a solitary island. It is another major hub in our supercluster, connected to us and to countless other galaxies by rivers of hot, thin gas we now know are there. This mental shift is profound. We are not simply looking out at the universe. We are looking out from within its architecture, our solar system, our planet, and the very eyes you are using to observe are all products of this flowing network. The atoms in your body were forged in stars that were themselves born from gas delivered along these cosmic channels. When you look up, you are not a separate observer viewing a distant scene. You are the universe itself in one particular location, looking back along the pathways of its own construction. This transforms stargazing from a passive act into an exercise in cosmic cartography. The constellations become local landmarks within our galactic knot, while the deep black gaps between them frame the outlines of the vast intergalactic continents we are just beginning to map. It invites a quiet, humbling realization. The majesty of the cosmos is not only in the brilliant points, but in the hidden, connecting fabric that gives them meaning and purpose. This luminous web is the true context for our existence, the universal stage upon which every story, including our own, unfolds. The journey to see the universe's skeleton has been a masterclass in scientific perseverance. It began as a theoretical dream, a beautiful pattern emerging from equations describing gravity and the aftermath of the Big Bang. For decades, the cosmic web was a ghost in the machine, a structure we knew must exist because the galaxies we could see were arranged in ways that demanded it. The supercomputer simulations gave that ghost a shape and a physical form, predicting not only where the filaments should be, but also the faint, specific glow of the gas within them. These digital universes provided the essential roadmap. They told observers where to look and what to look for, transforming a search in the dark into a targeted hunt. The final, breathtaking confirmation came from a new generation of telescopes and ingenious techniques. By using the combined light of distant galaxies as a cosmic lamp, and by developing instruments sensitive enough to isolate a single, telltale color from the overwhelming darkness, we finally turned on the lights. The faint fluorescent strands snapped into view, exactly where the simulations had foretold. This was not a lucky accident. It was the result of a perfect, iterative dialogue between prediction and observation, between the theoretical universe inside our machines and the real one above our heads. The collaboration between simulators and observers has given us three monumental truths. First, the cosmic web is undeniably real. It is not a metaphor or a convenient model. It is the observed, physical architecture of the cosmos on its largest scales. Second, those glowing filaments solve the long-standing mystery of the missing baryons. They contain the majority of the universe's normal matter, hidden in plain sight as a diffuse, superheated plasma. Third, and most profound, this web is not a static sculpture. It is the dynamic framework upon which galaxies are built and fed. It acts as the universe's circulatory system, with rivers of primordial and recycled gas flowing along invisible dark matter channels, sustaining galactic growth across cosmic time. The basic picture is now gloriously clear. We live within a connected, flowing universe, yet this discovery is not an ending. It is a magnificent new beginning. Our map is still coarse, a sketch where a detailed portrait is needed. The precise physics governing the flow, the temperature, and the enrichment of these cosmic rivers remains the great work of the coming decades. Every new observation with telescopes like James Webb and Roman, every more sophisticated simulation, will add finer strokes to this picture, revealing not just where the web is, but precisely how it brings a universe to life. The faint glow between the galaxies is a permanent reordering of our place in the cosmos. This discovery does more than solve a puzzle about missing matter. It rewrites the story of our home. We are not merely inhabitants of a galaxy, floating alone in a dark sea. We are residents of a specific, luminous thread within a universal tapestry, a living point along a river of gas that has been flowing for billions of years. Our solar system, our planet, and every element that makes us were gathered and delivered by this grand architecture. We are not just in the universe, we are of the web, products of its patient, connective logic. This perspective collapses the distance between the vast and the intimate, placing our local story directly within the flow of the largest possible narrative. The loneliness implied by the night sky is an illusion, replaced by the profound understanding that we are embedded in a continuous, breathing structure. The faint strands are a reminder that isolation is a cosmic impossibility. We are all connected by the same ancient, luminous currents. This realization is the true gift of the discovery, a new origin story that ties our existence to the fundamental architecture of everything. The journey, however, is just beginning. The ghostly images we have today are only the first blurry sketches of this magnificent design. Within the coming decade, a new fleet of space observatories will transform that faint, statistical glow into a high-definition map. Telescopes like the Nancy Grace Roman Space Telescope will chart the web's full expanse, while advanced X-ray observatories will take its temperature and measure its pulse. We will move from confirming the web's existence to reading its history in detail, tracing how its flows have shaped every galaxy, including our own. This is not the end of an exploration, but the opening of a new era of cosmic cartography. The story these instruments tell will be the most complete picture of our universe's structure ever assembled. To follow that story as it unfolds, to see the next ghostly filament snap into brilliant clarity, is an invitation extended to all of us. Stay curious, look up, and follow the journey of these new eyes on the sky. The next chapter in mapping our cosmic home is being written right now, and it promises to reveal the universe not as a collection of points, but as a single, luminous, and connected whole.